So our last couple of sections, as you remember, you have the sheets. We've talked about different types of numbers, and in particular, the last two sections we dealt with the rational numbers. The rational numbers are things that you can write as fractions. When you make a decimal out of them, what happens when you make a decimal out of a rational number? What are the options? It either repeats or it terminates. Yes. Okay, that's our rational numbers. Then there are other types of decimals. The decimals that don't repeat or terminate, those are called irrational numbers. And so when we smush together the rational and the irrational numbers, we get the set of numbers that we most commonly used, and they are called the real numbers. Okay, the real number system is kind of what we operate in. It's called real numbers because that's what we use in our day-to-day life most of the time. Now, if you took some algebra, you know that there's number systems beyond the real numbers that actually come into play in certain situations, but that's not our concern. So this chart on this page is just kind of a real quick review of where we have already been in our different number classifications. So we started out in our very first section. We've used them before in this class, the natural numbers. The natural numbers start with 1, and then they just proceed by increments of 1, 2, 3, 4, 5, forever and ever. And then the whole numbers, the only difference between the whole numbers and the natural numbers is that there is a 0 at the beginning of the whole numbers, which you think that's kind of not a big deal, but in human development, that took thousands of years for people to develop the concept of 0. So that's probably why it gets its own set. The integers are the whole numbers and also the negatives. Okay, we mentioned those briefly. And then we used the integers to make the set of rational numbers. And here's the set builder notation that you have in your notes. It's the set of fractions. And the only limitation on my fraction is that the denominator b cannot be 0. And then finally, what we talked about last time, we talked about the irrational numbers. Those primarily the big example in this class, because we are just doing a super quick survey of all this, is any square roots that don't turn out to be perfect squares. So just as an exercise to go through the number classifications, I've got a problem, you've got a problem. We're each going to do one of these. And the example looks like this. I'm giving you a set of numbers. There's 1, 2, 3, 4, 5, 6, 7. There's 8 numbers in there. And what we're going to do is we're going to classify each of the numbers by their different category. Okay, so we're just going to go one at a time. You're going to help me out, and you can use the table that you have in front of you to help make these distinctions. But we're going to start with -7. -7 is the first number that we're going to deal with. Now, -7. Which number classifications would you throw -7 into? Okay, it's an integer for sure. Okay, it's not a natural number. It's not a whole number. Those don't count the negatives. Great. What else is -7 a part of? Yeah, because you could write it as a fraction. It's -7 over 1. So it's a rational. Because it's rational, it's not irrational. You're either one or the other. And then the last number system it's going to be part of? Yeah, and just to give you the spoilers, all the numbers are real numbers, right? There's nothing that we can find here. So we're just going to I'm just going to put down here at the bottom all of them. All right, the next one is -3 over 4. So again, help me out. What number system, or excuse me, what number sets is -3 over 4 going to be part of? Yep, it's a fraction. So -3 over 4, because it's a rational number, it's not an irrational number. So we're done with that one. I already told you all of them are real, so that's implied. The next number is 0. What number systems are 0 in? Okay, it's a whole number. Yep. It's an integer, 100%. One more. It's a rational. Yeah, you can write 0 as 0 over 1. And of course, it's a real number. All of them are. I'm not going to say that for every single number. Okay, the next one is 0.6 with the bar over it. Remind me, please, what does the bar over the 0.6, what does that mean? That's the digit that repeats, yes. And so 0.6 repeating, what number system does that belong in? Yep, it's a rational number, so 0.6 repeating. And again, it's a real number. Square root of 5. Square root of 5 is 5 a perfect square? Can I take that square root and get a whole number? Nope. So square root of 5 is what kind of number? Perfect. Well said. It's irrational. So we're going to put that right there. Pi, our good buddy. Ratio of the circumference to the diameter of a circle. What kind of number is that? Yep, again, that's an irrational number. Great. Two more. 7.3 is what? Rational. It's a terminating decimal, so rational. And then last but not least, the square root of 81. The square root of 81 is what? Okay, yep, it's a natural number because it's 9. So what I'm going to do is I'm just going to come over here. Square root of 81, that's 9. So I'm just going to change it because we would always simplify it. But just for kicks, this is a problem from the book. The book wrote it square root of 81. So it starts off as a natural number. What else is 9? It's a whole number. Yes. What else is 9? It's an integer. Yes. And then what else is 9? And it's a rational. And of course, all of them are real numbers. There we go. That is the exercise, just classifying. The value in that is it's just helping you get used to the different number systems. That's all, so that you can tell the difference. So flip the page. Oh, this printed out double-sided on us today and upside down. I don't know who had that setting on the copier, so that makes it fun for us. Sorry about that. That was unintentional. Exercise 1, which is, I guess, at the bottom of the flip side of that page. So it's the same sort of problem. You've got -9, -1.3, 0 again, 0.75 with a bar over it, square root of 9, square root of 10, 9.57, square root of 41. So there you go. All right, I'm just going to get started with this problem. So you check your answer with mine. If you're still working, keep working. So I'm just going to put the numbers in their respective places. So I'm going to start with -9. So -9 is going to be an integer, and then it's going to be a rational number. And then like the last problem, just to save ourselves a little time, I'm just going to write that all of them are real numbers. Okay, so there's not one of them up there that is not a real number. So we can just take that for granted. It's off the board. All right, the next one is negative 1.3. That is a terminating decimal, so that goes in the rational number file. And if you're rational, you're not irrational, you're one or the other. We good so far? Anybody got a question, comment, or concern? Remember, stop me. I'm here for you. I'm having a great time, but I want to make sure that you leave here feeling just as good as I feel. So 0. Because irrational. So the question, in case you didn't hear it, is why is it not irrational? Irrational numbers, when they're written as a decimal, they do not repeat and they do not stop. They go on forever and ever. 1.3 stops at 3. It's a terminating decimal. That means it is a rational number. The next number is 0. 0 is a whole number. 0 is an integer. 0 is a rational number because it can be written as 0 divided by 5 or whatever, and then it's a real number. 0.75 with the bar over the top. Just like the last problem you told me, the bar means that the 7.5 keeps repeating. And so since it's a repeating decimal, that means it's a rational number. So 0.75 with the bar over that whole thing. Square root of 9, this was the little bit of trickery from the book's problem. Square root of 9 is 3. It's a perfect square. It's on that list that we generated a couple sections ago. So that is going to be a natural number, and then a whole number, and then an integer, and then a rational number, and it's a real number as well. We've already covered that. Square root of 10, how about square root of 10? Is that a perfect square? So when it's not a perfect square, what kind of number is that? Irrational. Great job. I appreciate that. 9.57. It's for the same reason as negative 1.3. It is what kind of number? Rational. It is a terminating decimal. So 9.57. And then last but not least, the square root of 41. Is 41 a perfect square? Nope, it's not. So that is going to be an irrational number. Anybody got any questions about the different number systems before I move on to the properties that real numbers have? All right, so now that we have developed this whole new set of real numbers, which is every number that we can possibly think of comes along that they have some certain properties that we can take advantage of. Some of these you've probably heard of if you've had any sort of introductory algebra course. You definitely use them, although you might not be able to name them. So I'm just going to help you name them and remind you the commutative properties of our real numbers. Well, I want to help you remember this. Okay, so I'm just going to tell you the origin of the word. So we've got at the beginning of commutative, we've got the word commute there, C-O-M-M-U-T-E. Does anyone know what the word commute it means when you commute? When you commute to work, you travel, you're moving, right? So commute means to move. So the commutative properties mean the properties that allow my numbers to move. And there's two, okay? There is the commutative property of addition. And I'm just going to use general letters here because any pair of numbers does this. What the commutative property says is if you have A plus B, then that is going to be the same thing as if I move them around, that's B plus A. Which we're thankful for that when we go to the grocery store, right? If we buy our lettuce and then bread, we wouldn't want the price to be different if we bought bread than lettuce. Like that would really make grocery shopping a wild experience. Okay, so the commutative property of addition just means it doesn't matter what order that you add things up, you're always going to get the same result. And the same thing is true for multiplication. Multiplication just says if I have A times B, then that's the same thing as B times A. Again, that's something we take for granted. We never even think about the fact that it doesn't matter what order we do things in. But I'm going to skip down to example 2. When I redo these notes, I'm going to change example 2. Instead of saying what operations on integers are commutative and associative, because I just gave away that it's adding and multiplying that are commutative, I'm going to ask you what operations on integers are not. Okay, so what are not commutative and associative? So let's think about subtraction. Is subtraction commutative? Well, I've just spoiled the surprise. I've said it's not, but how do we know? Give me an example that demonstrates that subtraction is not commutative. Okay, well, we're gonna do subtraction. Okay, so but we'll get to multiplication because you're right. So 50 minus 10, I'm gonna use your numbers. You're 100% correct. 50 minus 10 is what? 40. And when I reverse it, you're just a step ahead of me. 10 minus 50, when I reverse those two things and I'm subtracting, what's 10 minus 50? Negative 40. So we can see right away subtraction is not commutative, right? So that's you just proved it. You found an example that violates the commutative property. Subtraction is not commutative. And we could also say, I could do an example, division is not commutative either. So for instance, if I had let's just do it like this. So this is subtraction. Division. Division, if I have 4 divided by 2, 4 divided by 2, your calculator will tell you that's 2. But now when I reverse the order, 2 divided by 4, what's 2 divided by 4 when you throw that down? It's a decimal. That's 100%. It's point something. Yes, it's 0.5. Yes, I love it. Yes, it's point something. I'll give you credit for that. 100%. So subtraction and division, order does matter. Okay, so that becomes an important point for us, that those are not commutative properties. And we'll come back to the associative property, but first I have to tell you what the associative property is. So let's go up to the associative property. When you're associated with something, like if you're part of an association, your homeowners association at wherever you live, if you have one, to be associated with something means to be grouped. So whereas the commutative property deals with moving things, the associative property deals with grouping them. And same two properties are associative as commutative. So let me just show you what I mean right here. So if I have this problem right here, a plus b plus c, I'm adding those 3 numbers, a, b, and c. It doesn't matter what the values are. This works for any numbers. I'm not going to change the order, but what I am going to do is I'm going to change the grouping, and I'm going to put the A outside, and then I'm going to have the B plus C inside, and those will be the same thing. So that's the associative property for addition. Notice we don't mix operations. It's not adding and subtracting or anything. It's just addition. And then the same thing is true for multiplication. So for instance, for multiplication, if I had A times B in the parentheses and then C outside, well, that's the same thing as I have the A. So notice in both my examples, the order of the A, the B, and the C has not changed, right? This is not commutative. Okay, the A, the B, the C are all still in alphabetical order on both sides of the equal sign. What's changed is where the parentheses are. And that's a perfectly legal maneuver if you have adding and if you have multiplying. So just like we said a moment ago for subtraction division, I'm not going to do both, but I'll do a subtraction example. But division isn't either. So our subtraction and division are not associative. I mean, so just any 3 numbers you want. These are going to be my 3 numbers. It doesn't matter. You can do this with your own numbers. If I have 9 minus 5 in parentheses and then minus 2 outside, I want to know, is this equal to, so I'm going to put an equal sign with a little question mark. I want to know, is this equal to, and I'm running out of room. Sorry, I did not budget right here. 9 minus 5 minus 2. Oh, almost just enough room. So again, notice I've not changed the order of the numbers at all. 952, 952 on both sides. All I've changed is the grouping. Well, let's see. Do I get the same thing on both sides? Well, 9 minus 5 in the parentheses on the left, that's 4. And then 4 minus 2 is 2, so I get 2 on the left. And then on the right, the 5 minus 2, that's 3 in parentheses. So then 9 minus 3 is 6. And we see that those two things are not equal. So subtraction is not an associative property. Subtraction, it matters what order, it matters what the grouping is. Both of those things are important. Same for division. We could make up numbers, but you can do that if you're really curious when you get home and you're doing your homework. Any three numbers you pick and you group, when you divide them, it's going to be different depending on the grouping. You with me so far? Again, these are things we take for granted. You do all your arithmetic. You've done your arithmetic your whole life, and maybe not even known that these things existed, but they're there, they're present. All right, the distributive property, this is one, if you've taken any algebra, you know backwards and forwards what the distributive property says. The distributive property is another way to get rid of parentheses rather than doing the order of operations. So for instance, if I have A outside some parentheses and inside I have B plus C. This also works with subtraction. Okay, it doesn't matter. The distributive property says, well, instead of doing what's in the parentheses first and then multiplying, what I can do is I can take the A and I can multiply it by both terms inside. So we can have A times B plus and then A times C. So here's what I would like you to do, just as a way to verify. I want you to trust me, not just take my word for it. So here is an example. I want you to do this both ways. I want you to do this with the numbers by distributing, and then I want you to do this by following the order of operations, just to confirm that you get the same thing either way. So here's an example. I've got 5 and then 6 plus 8. So what I want you to do, I'm going to do this over to the right. I'm going to follow the order of operations, and then going downward, I am going to distribute, and we're just going to confirm that we get the same value either way. I'm going to give you 45 seconds to go ahead and do that. All right, so doing this first by following the order of operations that we talked about in a previous section. Order of operations says do your parentheses first. And so 6 plus 8, that gives me 5 times 14 when I do the parentheses first. And then 5 times 14, you could throw that down into your calculator. That gives you 70. Doing this by the distributive property. Okay, this is another way to resolve the parentheses in this case. Well, the distributive property says first 5 times 6. 5 times 6 gives me 30 plus 5 times 8. 5 times 8 gives me 40. And 30 plus 40 is 70. So notice we just verified the distributive property. We got the same result regardless of what we did. Okay. Still, we doing okay? Just showing you some properties. Now, those are the properties that we are familiar with. There are a couple properties of real numbers that we are not familiar with. So if we can find the next page on this weirdly printed packet, here it is. It's the page that at the top says closure. So if you find that. The closure property. Now, this is a fun one, okay, I think. The closure property means this. If you have an operation performed on any two elements of a set, and the result is an element in the set, then that set is called closed under the operation. So again, if you have a set of numbers and an operation like addition or subtraction or multiplication, division, whatever operation you're dealing with, okay? If you take two elements of the set and you perform the operation and you always get an element in the set, then it's called closed. So for instance, you might be thinking, well, that sounds great, but I have no idea what it means. Well, here's my example. Are the whole numbers closed under addition? And what that means is whenever I take two whole numbers, do I get a whole number? Now, from the first page of our packet, the whole numbers are the numbers that start at 0 and go 1, 2, 3, 4, 5, 6. So let's just take some examples. We can't technically prove this. We don't have the math background to do that, but we're going to demonstrate one way or another what we think. We're going to use some pattern. So give me two whole numbers. 7 and 8, and you're saying 10 and 12. Okay, so 7 and 8. When I add 7 and 8, those are both whole numbers. We get 15. Is 15 a whole number? Okay, so far we have evidence that leads me to believe that closed. So let's try again. So the next pair I heard was 10 plus 12. Those are both whole numbers. 10 plus 12 is 22. Is 22 a whole number? Yes, let's just try one more, and then we are going to make a hypothesis, and that's going to be where we end our discussion. So here's my pair. Let's say that we have 11 plus 35. Those are both whole numbers, and 11 plus 35 is 46. Is that a whole number? Yes. So what do you think? Are the whole numbers closed under addition? If you take two whole numbers and you add them, do you always get a whole number? Yes. Okay. So are they closed? Yes. And here's why. The y is the result is always another whole number. That's what it means to be closed. All right, well, you try, do your best. You might get the answer wrong. Remember, that's okay. Doesn't mean there's anything wrong with you. Okay, exercise 2. Are the whole numbers, those same set of numbers we were doing, are they closed under subtraction? Meaning if I subtract two whole numbers, do I always get another whole number? So I'm going to give you a minute or so to make a hypothesis on that. Write down some examples, what you think. So what do you think? Are the whole numbers closed? Do you always get a whole number when you subtract? No. Why? Give me an example that violates it being closed. 2 minus 4. 2 and 4 are both whole numbers. I agree. Let's subtract them. When you subtract 2 and 4, what do you get? Is negative 2 a whole number? No, this is not a whole number. And so for that reason, are the whole numbers closed under subtraction? The answer to that is no. The result is not always another whole number. Great. Excellent work. If you didn't quite get that, that's okay. Now you learned a little something. You see how this works. So what if I change the set? So exercise 3 is the same question, except instead of whole numbers, you're asked, are the integers closed under subtraction? So again, give that a little try. Subtract some integers and determine, do I always get an integer? Yes or no? Let's see. So what do you think? When you subtract two integers, do you always get another integer? Yeah, that's actually what exercise 2 was kind of leading to, is when we did 2 minus 4, we ended up with -2. And while -2 is not a whole number, it is an integer. So that was kind of why I was leading us. So let me just pick some examples, and then we can be good. So for instance, 5 minus 3, those are both integers. When I subtract them, I get 2. That's an integer. Okay. 7 minus 10, both integers. When I subtract them, I get -3. That's an integer. One more example, -5 minus 4. -5 and 4 are both integers. When I subtract them, I get -9, which is another integer. So by doing a few examples, I come up with yes. And again, I'm going to write down why so you have it in your notes. The result is always another integer. So that's possibly a property that you hadn't heard of before. Okay, so here's another property. Maybe, I mean, I'm sure you've used this property, but you maybe didn't know that, math people, because we love to have a name for everything, gave it a name. The next property of real numbers is called the identity property. And what the identity property it means is this: given an element of a set, so you pick any number, and identity is an element that produces the given element when the operation is performed. Now that sounds like a lot of words, so I'm going to try to make this a little easier after you filled in those couple blanks, because I think the identity property is a pretty straightforward one. So let me ask you this question: what is the identity for integers, or actually for any of the sets of numbers? What's the identity under addition? Meaning, if I start out with an integer like 10, what do I add to 10 to always get the same thing? 10. 0. Yeah. What's the identity under addition? The identity is 0. So here's a couple of examples just to show you. If I start off with 14, 14 plus 0 is 14. I end up with the identical thing. That's why it's called the identity. What I start with, 14, and what I end with, 14, are identical. If I have -6, -6 plus 0 is going to be -6. Again, what I start with and what I end with are identical. That's what it means to be an identity. So that's the identity under addition. So exercise 4, your exercise, I want you to answer the question and come up with just a couple quick examples like I did for what's the identity for integers under multiplication. What will you multiply by to end up with the exact same thing that you started? Don't shout it out, write it down, and then we'll compare notes. And what is the identity under multiplication? It's what? 1. Yes, the identity for multiplication is 1. Now, I don't know what your examples are. They're going to look something like this. If you have 15 times 1, 15 times 1 is 15, whatever numbers you picked. -7 times 1 is -7. Again, it's called the identity because what you start with and what you end with are identical. That's why it's the identity. Excellent. We doing okay? Just going through some trivia of real numbers just so that you can feel really happy going into the Thanksgiving break. All right, here's the last property of real numbers. And then I've just got one more problem for each you and me to practice these properties in a little bit of a different context. Okay, so the last property is called the inverse property. Two elements in a set are inverses if the operation is performed and the result is the identity element, which we know the identity for addition is 0 and the identity for multiplication is 1. So, example 5. This is my example. Does every integer have an inverse under multiplication? Okay. So what that means is if something's going to, if two things are going to be inverses, let's start with an integer, 5. Two things are inverses. I'm going to put a little box right here because I don't know what the inverse is. Two things are inverses if when I multiply them, I get the identity, which is 1. So the question says, if you start out with an integer, -5, does it have an inverse? Meaning, does it have another integer that when I multiply it, I get 1? Well, forget the set of numbers for a minute. What is the inverse of 5? 5 times what is going to give me 1? 5 times 5, you're close. You're on the right heading. I understand where your mind's at. 5 times 5 is 25, but it is related to 5. But it's not going to be 5. There's a 5 in it. There's a 5 in the inverse. All right, well, let me offer you a little help. Okay. 5 times 1 over 5 is going to be 1, a fifth. And 1 over 5 is 0.2. You can verify with your calculator. 5 times 0.2 is going to give you 1. Well, here's the question then. Is 1/5, is that an integer? What kind of number is 1/5? It's a rational number. So does every integer have an inverse for multiplication? And the answer is no, because the inverse is a rational number. Well, try the next one. I think you could do the next one. Does every integer have an inverse under, now this time, addition? Okay, so pick an integer and then ask yourself, what do I have to add in order to get the identity, in order to get the identity for addition? So give it a try, see if you can come up with it. And remember, if you can't, it's okay. That's why we're here together. So what's an integer you picked? Somebody give me your integer. 5. Okay, you picked the same one as me for the previous problem. I love it. Good. Great minds think alike. All right, so 5 plus, here's my box. 5 plus what equals 0, which is the identity for addition? In this case, -5. basically the opposite of whatever you picked. If you picked 12, it's negative 12. If you pick negative 17, the inverse is going to be 17. Is this number in the box, is this another integer? Yes. So does every integer have an inverse under addition? And the answer is yes, because 5 and negative 5 are both integers. That's why. Now that last one gets a little, understands a little headier. It's a little harder to understand. We're getting into a little bit of more advanced elements of number theory, but it's good to have awareness. All right, so what we're going to do is we're going to flip the page, and of course flip the page and rotate it because it printed weird. Okay, and we're going to finish off with if we had more time, we would talk about what's called finite math. And this is kind of the beginning of a branch of mathematics called finite math. And what finite math is we develop a math system that instead of using the whole numbers, which are, they never end, or instead of using the integers, which never have an end, we use a set of numbers that is finite. It has an end. So for instance, we're going to do this thing called clock arithmetic. Now I know everybody has digital clocks, so we're not super familiar with clocks. So we're gonna practice a little bit. But so by the way, there's going to be a problem just like this on the test. I've got this problem right here that I'm going to do on the back page. The last problem for today is going to be very similar that you're going to do, and then there's a couple on the homework, and there's going to be one on the test when you take it the Tuesday after Thanksgiving. So put a little asterisk here, make sure that you understand what's going on here. So clock addition. So here's the first thing I want to know. Here's my clock, and we're going to talk about adding numbers on the clock, and we'll do some examples in just a minute. But what I wanted first to let you know is what are the elements of the set that I'm going to do clock arithmetic? Well, it's just the elements on the clock right there. It is just the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. There are 12 elements of the set that I'm going to do arithmetic with. So let's do some examples of addition on the clock. So for instance, here's a nice straightforward, you don't even need the clock for this one. But let's say I ask you to add 2 plus 3. What's 2 plus 3 going to give you on the clock? Yeah, if it's 2 o'clock and I say meet me at McDonald's in 3 hours, you're going to meet me at 1, 2, 3, 5 o'clock. Okay, as we count around. So great. That didn't even require the clock. Here's one that's a little bit more challenging. If it's 6 o'clock, and I say, meet me in 10 hours, what time is it 10 hours after 6 o'clock? Let's see if she is right. So here's my pen is on 6. That's why I put the clock right here. It's just so you can practice. Okay, so we're going to count 10. We're going to add 10 to this. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And where am I at? Just as I was told. 4. All right, well, here's a few for you to practice. Okay, I want you to try this because you may or may, I don't know how familiar you are with the clock. I'm old school. I'm 53, so we didn't have digital clocks back in my day. So here we go. So I want you to just do this addition. So there's 4 problems right here. Let's say you have 8 plus 7. Let's say that you have 5 plus 11. Let's say that you have 3 plus 12. And then last but not least, let's say that you have 9 plus 6. Go ahead and add those 3 things using that clock as we're getting used to this, what's called a finite math system. You don't need to know those words. I'm just letting you know what it is. All right, so help me out here. 8 plus 7. When I start at 8 and I go 7 hours, what is the result there? 3. Yeah, just in case you didn't get it. My green pen is on 8. I am now going to count 7 hops around. 1, 2, 3, 4, 5, 6, 7. We end up at 3. Great job. How about 5 plus 11? What do I get when I start at 5 and I go 11? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You're 100% right. 4. Great job. How about 3 plus 12? Where do I end up? Yeah, 3 plus 12. You made one circuit all the way around this 12-hour clock. So you're back at 3. And then finally, 9 plus 6 ends up being what? Okay, 1, 2, 3, 4, 5, 6. Ends up at 3. I don't know why so many of my examples ended up at 3. I just must have that on the brain today, but there we go. Right? You tracking with me on how to do addition on the 12-hour clock. Okay. It's a finite math system because you just keep going around and around and around in a loop there when you're adding. Now, what I did because I was bored is I then did your addition table, okay, for the clock system. And so how do you read the table? You read the table like this. If we were doing 8 plus 7, then I would say, okay, here's 8 over here. It's plus, the operation is printed right above, right between those number ones up in the corner. So 8 plus, and then I go over to 7, and 8 plus 7, just as you told me, is 3. And then 5 plus 11. Here's the number 5. I go over to the 11 column, and the result is 4, just like you told me. That's how you read the table. So I just took the time to go ahead and give you all the values for any pair of numbers that you could add in this system. And what we're going to do is, using that table and our ability to do this, we're going to answer the 5 questions down below about this. These have to do with the properties of numbers. Okay, that's kind of the whole purpose of this. Is it just gives us another way in a little bit of an easier situation to look at the properties of numbers. So example 6, what we're going to do is we're going to apply the properties of real numbers to clock addition. The A problem says, how can you tell that the set 1 through 12, those are my clock values, is closed? So this is what we're talking about, is closed for clock addition. Well, what did closed mean? Closed meant that if I started with 2 numbers on the clock and I added them, what would I get? If I start with a number between 1 and 12 and I add it to another number between 1 and 12, what will I always get if it's closed? You'll get another number between 1 and 12. So let's look in this table of values. All these values right here that we're looking at, are all those values from 1 to 12? Is there ever a 13 or a 19 here? No. So what we have is we have a closed system. If I take a number 1 through 12 on the left and I add it to a number 1 through 12 on the top, then the result is always a number 1 through 12. So I'm going to write that. All the results are 1, 2, 3, 4, ellipsis, 12. So it's closed. That's how I can tell. The B problem asks us to verify the following example of some property. That's where you're going to come in first, and then we're going to do the rest of the problem together. Looking at this, I have 2 plus 3 in parentheses plus 10, and then I have 2 plus 3 plus 10 in parentheses. This is an example of what property of numbers? What was that? Not the distributive. What did you say? The associative. Yes, this is the associative property. And we're going to see if addition in the clock system is associative. All right, well, let's do it. You told me in an example above, 2 plus 3 2 plus 3 is 5. So on the left, I have 5 plus 10. And either using the chart or using the clock, when you take 5 and you add 10 to it, what's 5 plus 10? 5 plus 10 is 3. Great. Well, I'm going to give you 30 seconds. I want you to do the one on the other side. 2 plus and then 3 plus 10 in parentheses. I'm sorry? We just did combine 5 plus 10. 5 plus 10 means I'm up on the clock, I'm at the number 5, and then I'm going to add 10 to it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I end up at 3. That's the result. So the clock is just providing the rule for what does it mean to add two things together. So on the other side, we start with the 3 plus 10. 3 plus 10, when I add that, 3 plus 10 is 1. And then 2 plus 1 is 3. So we got the same thing regardless of the grouping. So what we did is we just verified the associative property. Here's a fun question. What's the identity element? What is the element that when you add to any number in the clock system, you get what you started with? So looking at the table, I want you to hypothesize. I'm going to give you 30 seconds to look at the table, and I want you to decide what you think the identity element is. When you start with a number, is there something you add to it to get the same thing back? What is it? Sure, 12, going one full circuit around. In fact, we saw that in one of our examples up here, 3 plus 12. When we added 3 plus 12, what did we get? 3. Okay, so that's the identity element. So what is the identity element in this clock system? It is 12. And I'm just going to put a parenthesis for your notes. 12 is the element that produces the identical thing, or the identical value. Probably is a better math word, but you accept me for my imperfections, right? The D part, we're going to find the inverse for each element. Now, we're not going to do this for every element. We'll do this for a few because this system's a little large. I'm going to put a little arrow here because this takes a little more space than I left. I should have left a little bit more. So we're going to find the inverse of every element. So remember, the inverse is if I start with an element like 1, I want to know what do I add to 1 in order to get the identity, which is 12. So what plus 1 plus what equals 12? And looking up at the chart, what do you add to 1 in order to get 12? 11. So 1 and 11, what we say is these two things are inverses. 1 plus 11 gives you 12. So I'm just going to write out a few other examples, and I want you to write down what you think the inverse element is for each of these. So let's say that we have 2. 2 plus what? What's the inverse of 2? Then do 3. 3 plus what? And then I'll just 2 more. Let's do 8. 8 plus what? And then finally 6. 6 plus what? So find the inverse of those elements right there. All right, so 2 plus what gives you 12? 10. 2 and 10 are inverses because they produce the identity element. What's the inverse of 3? 3 plus 9 is 12, yes? What's the inverse of 8? 8 and 4 are inverses, yes. And then lastly, what's the inverse of 6? 6 is its own inverse, yes. 6 plus 6 is 12. Great job, everybody. Thank you. One more question, and then the last page is you. You're going to do all this same thing for a smaller finite math system. So the last one is pick 2 examples to verify the commutative property. So again, I'm going to draw a little arrow because I didn't leave myself enough room here. So I'm going to pick 2. You give me 2 numbers, and we're going to verify the commutative property. 2 and 6. All right, here we go. 2 and 6. So when I do this, first what I get is 2 plus 6. Well, according to my table or looking at the clock, what's 2 plus 6 going to give me? Okay, so here's 2, and then plus 6 is 8. Excellent. So I'll circle 8 up there. We'll come back to that. 2 plus 6 is 8. And then 6 plus 2. We are going to reverse it because that's what the commutative property says. So let's go back up to the table. I've got 6. This time I'm adding 2. And what's 6 plus 2? 8. Yes. So the commutative property holds for those 2 values. And in fact, the whole finite system would be commutative. Yes. All right. So flip to the last page if you can find it on this weirdly printed packet of things. This time what I've given you is a 6-hour clock. Instead of being 1 through 6, I made it 0 through 5, or I found an example that was 0 through 5. So it's the same sort of thing. First, what I want you to do is I want you to list the elements of the set. Then instead of a few examples, what I want you to do is fill in the table of values, your addition table, using the clock. And then answer the 5 questions. I'm going to give you 3 or 4 or 5 minutes to make as much progress on that as you can. I'm going to get a drink of water. And then if you have any questions, raise your hand. I will fly to you and we'll do our best. All right, let's see how you did. And if you got any questions, we can talk about them. So first, what are the elements of the set for this particular clock right here? Yep, 0 through 5. 0, 1, 2, 3, 4, 5. Those are the 6 elements that represent my 6 different hours. Excellent. So now I'm going to go down here. I'm going to use the clock if I need to. I'm going to fill in the table of arithmetic. So 0 plus 0, that's fun. That's 0. 0 plus 1, 0 plus 2, 4, 5. When I add 1 to these, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5. Now here's the fun one. What's 1 plus 5? If you are at 1 and you add 5 to that, you end up at what? 0. Yes, excellent. And now 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4, 5, and then 2 plus 4. If you're at 2 and you add 4, you end up at 0. And then 2 plus 5 is 1. That's how the clock is working for me. 3, I get 3, and then 4, and then 5, and then 3 plus 3. If I'm at 3 and I add 3 to that, I go 1, 2, 3. I'm at 0. And 3 plus 4 is 1, and 3 plus 5 is 2. 4 plus 0 is 4, 4 plus 1 is 5, and then 4 plus 2 is going to give me 0. 4 plus 3 is 1, 4 plus 4 is 2, and then 4 plus 5 is 3. So you see, doing arithmetic starts to get a little goofy when you're thinking circular on the clock instead of linear, like we think, when we're using the whole numbers or the integers or whatever. And then 5 plus 0 is 5, 5 plus 1 is 0, 5 plus 2 is 1, 5 plus 3 is 2, 5 plus 4 is 3, and 5 plus 5 is 4. All right, there's my arithmetic table. Now, whether you got all the way through that or not, do you see where those values came from? Are we doing okay? All right, there's a couple problems like this on your homework, so you'll get your chance to determine and practice. So now what we're going to do is, we're just like we did before, we're going to apply the properties of real numbers to these. So first off, looking at this table, is this a closed system? Is addition closed for this 6-hour clock? How do you know? You said yes, you're 100% right. How do you know it's closed? No matter what you add, you always get a number 0 through 5, right? You never get something different. That's how you know. Closed means, just to reiterate, closed means when you pick two elements, 0 through 5 plus 0 through 5, you will always get 0 through 5. You always get another element of the set. So how can you tell? Because in the table, there are all the results are 0, 1, 2, 3, 4, or 5. There's nothing any different. Great. Now we're going to verify the following property. And again, just to make sure you're awake, what is the property that I have printed right here? The associative property, once again. So when you take 3 and you add 4, 3 plus 4 is 1. And then 1 plus 2 gives you 3. That's what you have on the left. And then on the right, you've got 3 plus 4 plus 2 is 0. And then 3 plus 0 is 3. So again, we verified it. We got the same thing when we changed the grouping. That's no problem. What's the identity? What's the element that when I add it, I get the identical result? 0. Yep, this time 0. Last time in the other clock, since the numbers were 1 through 12, not 0 through 11, the identity was 12 because that took you all the way around the clock. This time, we don't have a element 6 in this one to take us all the way around, so the identity is 0, okay? And you can see that on the table right here. 0 plus 0 is 0. 1 plus 0 is 1. I started with 1. I ended with 1. 2 plus 0 is 2. Started with 2. Ended with 2, etc. 5 plus 0 is 5. Started with 5. Ended with 5. That means 0 is the identity. Now what we're going to do is for each of the elements, we're going to find its inverse. What is the value that when I add to it, I get 0? So let's start with 0. It's not really super interesting, but 0 plus what gives me 0? Yep, 0 is its own inverse. Okay. 1 plus what gives me 0? One plus 5 gives me 0. Yes. 2 plus what gives me 0? 2 plus 4 is 0. And then one more. 3 plus what is equal to 0? 3 plus 3. 3 is its own inverse. Now, we don't have to do 4 and 5 because we've already determined what their inverses are the first time around. And last but not least, we are going to pick an example to verify the commutative property. So somebody give me two numbers in this system. 2 and 5, all right? 2 plus 5. So when we do 2 plus 5 on the clock, when I start at 2 and I go 5, 1, 2, 3, 4, 5, the result is 1. So 2 plus 5 is equal to 1. And then 5 plus 2. 5 plus 2 equals, well, let's come back over here to the clock. 5 plus 2, 1, 2. 5 plus 2 equals 1. And so we have the same thing, and so we verified the commutative property. Does not matter what order you add two things in, you're going to get the same result.